This video will teach you about acids. There are 3 models for what acids and bases are, so I'm going to go through those with you. The first one that we're going to go through is the Arrhenius model, and this was the first model that existed for acids and bases. And in the Arrhenius model, acids and bases are related to what they do in water. In water, an acid will become H+, and in water, a base will become OH- hydroxide. So that's the Arrhenius model, only has to do with water. But acids and bases can exist outside of water. So that's where the Bronsted-Lowry model comes in. And this is the one that we will be using in class. And in this model, acids are H+ donors. In chemistry, H+ are also known as protons. So if you hear me refer to H+ as protons, that is what I'm talking about. And that's because an H+ is singularly a proton. If you think about the atomic structure of hydrogen on its own, it's got 1 proton, 0 neutrons, and 1 electron. So to become H+, it loses its electrons and thus is just a proton. So that's how it's referred to. And in the Bronsted-Lowry model, bases are H+ acceptors, meaning the structure will take the H+, whereas the structure for an acid will give away an H+. And you can see how that's different than the Arrhenius model, because in the Arrhenius model, it's just talking about water. The third model for acids and bases is the Lewis model. This is the newest model, and it's a really useful model. We're not going to do it in our class, but when you move on to higher level chemistry classes, generally they work off of the Lewis model for acids and bases. These are all the same, it's just a different way to think about them in each setting. So in the Lewis model, acids are electron pair acceptors. That's different than an H+ acceptor. I'll show you on the example that we're going to do. And bases are electron pair donors. So again, we're not going to use the Lewis model in this class, but it is handy to know. So why do we have these things that happen? Because of polarity and dissociation. Dissociation means to detach or split. So if we're using the Bronsted-Lowry model, an H+ donor for an acid means that the H+ will dissociate, will detach from the structure. It's really key that you understand that this only happens with polar hydrogens. Really important. So let's do an example of a strong acid, which we'll talk more about. Hydrochloric acid, you've seen this, HCl. The H+ and the Cl, the H and the Cl will split apart from each other, and the electron that was between them in the bond will go with chlorine, and the H+ will have no electron. They split apart. They dissociate. All right, let's do another example. Formic acid. Formic acid has the structure that many organic acids have, this COOH group. And for formic acid, the other side is just a hydrogen. There's going to be some dissociation because it's an acid. So take a second, guess which hydrogen is going to dissociate. If we do the polarity of our structure, there is only one hydrogen that is polar, this one. So that's the one that dissociates. And what you get is H+ in solution, aqueous, and the resultant structure. And now this oxygen has a formal negative charge. Formal meaning it's not partial. So here the negative charge is partial. And remember, there are electrons between these two atoms. And so what's happening in this situation is the electrons, both of them are staying with oxygen. That's how hydrogen gets its plus charge, and that's how oxygen gets its formal negative charge. So you might be asking yourself, what about the Lewis model? So I'll just talk about that really quickly so you can see. In the Lewis model, acids are electron pair acceptors, and bases are electron pair donors. So if we put the electron pairs, pair meaning 2, around our negatively charged oxygen here, it has an electron pair that it can donate to a bond. And it would donate to an H+, which has no electrons around it. So you can see that acids are electron pair acceptors because it will accept, I'm going to draw it here, it will accept this pair of electrons. And the O- has 2 electrons to donate into a bond. So it's into a bond. So the Bronsted-Lowry model and the Lewis model are not necessarily different than each other. It's just a different way of thinking about it, even though the words are switched around. In the Bronsted-Lowry model, this acid over here is donating this H+. And the base that is formed over here has a place to accept an H+. It's just a different way of thinking about it. So we're going to do it based on the Bronsted-Lowry model. So don't worry too much about the Lewis model if you don't understand it. Okay, a few more things here. Most acids, not all, but most acids dissociate only one hydrogen. That's it. Most acids only dissociate one H+. And it bears repeating that polar hydrogens, that is an H with a partial positive charge, can dissociate, whereas nonpolar hydrogens cannot dissociate ever. They cannot do it. There has to be some sort of uneven balance, which we get in polarity, where it is easy. It doesn't require very much energy for this H to leave. Whereas here, where the electrons are being shared evenly, that would require a lot of energy to remove that hydrogen, because there are attractive forces holding it on. Whereas here, when the electron is more towards the oxygen, it's kind of already loosely there anyways, so it doesn't require very much energy to get that bond to break. And oftentimes, and this is where the Arrhenius model comes in, water has enough attractive force to pull this off. So sometimes you'll see H+ written like this. And this means that the H+ is bound onto the water that it's in. This is aqueous. So that structure is kind of like this. This is unstable. Thus, this H+ can come on and off. So this is kind of where you get the Arrhenius model. So you can see that all of the models really all work together. It's just you go from something very specific, like the Arrhenius model, only about water, to something extremely general, like the Lewis model can be applied to anything, acids that don't have H+. All right, you should be able to do your homework now.